Hello, everybody. Over the last couple of months, I've been taking a course on physical biochemistry, and something really interesting that I've come across is how diffusion simulations can lead to better chemotherapy. There is a pretty big list of cancer treatment options, but surgery and chemotherapy stand as the most robust and prominent options. Chemotherapy specifically is noted to, on average, prolong survival by 14 months and increase 5-year survival rates by up to 8%. It exists as the most prominent option in stage 4 cancer treatments. Most forms of chemotherapy are administered intravenously, but a few therapies involve using short, subcutaneous needles that will lead into bodily tissue where cancer supposedly exists. We will be focusing on the latter kind of treatment. Unfortunately, as most of you are aware, chemotherapy is one of the most dangerous double-edged swords. While only occasionally curing cancer, chemotherapy will always involve debilitating side effects. Now, why is that? While chemotherapy works really well to kill and destroy tumor cells, it attacks both healthy and tumor cells alike. If chemotherapy is injected off-target and affects more healthy cells than tumor cells, patients will observe worse outcomes than prior to treatment. Now, that said, there is a lot of difficulty in the injection of drugs, since after injection, drugs do not stay in tissue but will diffuse across a distance. If it's very important to carefully measure where the chemotherapy ends up, how can we handle where it goes with more accuracy? Luckily, mathematician Fick came up with an equation that can accurately estimate how far and at what time a molecule or object can go. But the most important measurement that gives us these models is the diffusion coefficient, and as it stands, it's largely unavailable. Diffusion coefficients for specific molecules can be measured in specific environments with the assistance of fluorescence correlation spectroscopy. Now, how the technique goes is a fluorescent molecule is put into a sample and its fluorescence is measured across time. When the sample's fluorescence decreases, we can safely assume that the number of molecules in that sample decreases. The number of molecules that leaves per millisecond can then be used to determine the diffusion coefficient. To measure the diffusion coefficient of a drug in tumor tissue, which is what we specifically need for our studies, we'll use red and green fluorescent proteins, which are fairly small and similar in size to chemotherapy agents. They will then be subjected into a sample of tumor tissue, and using fluorescence correlation spectroscopy, we can ultimately determine the diffusion coefficient. With that experimentally determined diffusion coefficient, we can then substitute that value into our diffusion equation on the right. Our models will ultimately end up to look like this graph. We can see how far the travel distance depends on the concentration of the dosage and how long the molecule incubates. Now, an analogy can be made to food coloring spreading throughout water. As food color is dripped onto a surface, it's going to take time to move throughout the system. And as we see in this picture, the further that it moves, the fainter the color grows from its initial point of entry. We can think of drugs and tissue in that same manner. The black line on the bottom of the graph represents a target concentration that's needed to kill the cancer cells. The intersection between the curves and that black line gives us an idea of how far the right concentration of the drug reaches. If we refer back to the food coloring model, we can relate target concentration of color. We want our target concentration, or our color, to just meet the right location without spreading too far or too short. By doing that, we can make sure our colors don't spill onto each other, or we can also minimize how far dangerous chemotherapeutic drugs move throughout our body. So, while all of this is just speculation and honestly isn't really backed by cold hard evidence or repetitive trials, it's something interesting to note. And I feel that it's something that can turn chemotherapy much safer than it currently is. Thank you all for listening, and I hope you learned something new from this. If not about curing cancer or trying to make chemotherapy much safer, maybe it could be about how physical chemistry might not be so daunting or might not be so uninteresting after all.